History. Some books do capture it as thermochemistry, and then others do capture it as energy and energy changes. So thermochemistry is more like a word that is used to describe energy and then energy changes. But what is this whole thing about thermochemistry? So the end of the lesson or the whole topic, what are we going to be looking at and what are we going to be studying? Now let me start by indicating here the topic thermochemistry. Then we can look at what thermochemistry is, and then we can effectively start with the lesson. So the topic is thermochemistry. Thermochemistry. Now, what is this whole thing about thermochemistry? So before you left for school, we studied heat. I remember very well I taught you heat. We did a couple of things under heat and all of that before you went back to school. And that's the reason I actually chose this topic, so that it'll be very easy for me to connect it to this one. And then we can also continue from there when we are done with what you need to know. Now, so when we say thermochemistry, it is just a branch of chemistry that looks at heat changes that occur during chemical reactions and physical changes of matter. So let me say a branch of chemistry that focuses on heat changes that occur during chemical reactions and physical changes of states. So in simple terms, we are trying to look at this branch of of chemistry that studies how much heat is absorbed or released when substances are reacting or when substances change to form new substances. Okay, in simple terms, how much heat is absorbed or released when substances react or change to form new substances. When we talk about a reaction, because you know that in chemistry a reaction is simply a transformation of one substance into new substances. So when chemical reactions are taking place, or when physical changes of matter seems to be taking place, there are instances where heat will be absorbed into the system, and there are instances where heat will be released into the system. So this takes us to what we know to be exothermic and then endothermic what reactions. Now, for example, when you are when you are burning wood, heat is released to the surroundings. Very soon, we are going to understand what surroundings mean in the context of chemistry. So, when you are burning wood, heat is released to the surroundings. So, we say that a reaction is exothermic because the heat is released to the surroundings. But when you bring ice out of your fridge, the ice begins to melt. What is happening is that the ice is absorbing heat from the surroundings, which is breaking the bonds of the atoms and then resulting them to move away from each other, or sorry, from one another, which results in melting. So that's essentially what we talk about when we say thermochemistry. How much heat is absorbed or released when substances react or change to form new substances. So let me cite one or two examples here for you. So example, I can say that during combustion, and combustion is a term used to describe burning. Okay, it's a more scientific term that is used to describe burning. So during combustion, we can say that heat is released, and so the reaction will therefore be called an exothermic reaction. So during combustion, heat is released, so the reaction becomes exothermic in nature. And during melting of ice, or during melting of ice, or let me say of shear nuts, heat is absorbed. And so the reaction will be said to be endothermic in nature. So that is simply what we are going to be looking at till the end of this lesson. So we are going to be playing so much with heat. But you see, we'll come to also look at another terminology associated with heat. And this is what is going to differentiate you from every other student. So there are times a book would say enthalpy. There are times the book would say heat. Are they different? If yes, what is their difference? Are they the same? We are going to be looking at all of that. Now, I mentioned something earlier that when a reaction is exothermic, it means that it is releasing heat to the surroundings. And then when it is endothermic, it means that it is absorbing heat from the surroundings. Now, the question you'll be asking is, if it is giving heat to the surroundings, where is the heat being lost from? Or how do we classify the area where the heat is being lost from? And if the thing is absorbing heat from the surroundings, how do we call what the heat is being absorbed into? I don't know if you're getting my question. Osman. Yeah. So one, you are losing heat to the surroundings. So there is something called surroundings. The aspects of that area, that environment that is losing the heat, what do we call it? We are going to be looking at that. And if the thing is absorbing heat into something, what is that thing going to be called? This is where the lesson takes us to system and surroundings. System and surroundings. Now, let's first begin with what a system is. Now, if I say that I want to study Osmond, I want to know how Osmond reacts or behaves to certain things. I want to know more about him. I want to know whether he studies. I want to know whether he's a serious young man. I want to know whether he's focused. I want to know how he behaves at home. I want to know more about Osmond. If I decide to study Osmond, then in science, Osmond becomes a system. So anything that does not form part of Osmond becomes Osmond's surrounding. So, for example, where you are sitting now, having the lesson, if I decide that I'm going to appear in your room and then analyze you as a human being or as a student, you are going to be my system because you are under study. You are being studied, you are being observed, you are being analyzed, you are being explored, you are being examined. You become a system. Anything around you that will not form part of you, or anything around you which I am not interested in studying, becomes part of your surrounding. So if there is any book in your room, the book becomes your surrounding. Your fridge forms part of your surrounding. Anything around you that does not form part of you, because I'm going to study you. So anything that does not form part of you becomes the surrounding. And then you that I am studying becomes the system. So in science, we say that a system is any part of the universe under study. In simple terms, any parts of the universe under study. Any part of the universe under study. So this is what we find ourselves. Anything you decide to examine or to analyze becomes your system. So you may not see under study, you may see words like under examination is the same thing. Under study, under examination, under observation, under analysis. Everything or anything you are studying becomes your system. Now, what then becomes the surrounding? So the surrounding becomes the outside of a system. The outside, let me say the outside, yeah. Oh, okay. Is it okay now? Are you sure? Oh, okay, I'm coming. Is it a bit okay? Oh, it's better now. Alright. So a surrounding is the outside environment of a system. So when we say surrounding, we are looking at anything that surrounds a system. Anything that surrounds a system is the surrounding. So these are very important things you need to know. And interestingly, for that matter in science, and you'll be doing this even to the upper level when you study engineering under what you know to be thermodynamics and all of that. You are going to be looking at this into details. You'd come to realize that there is a way a physicist views a system, and there's a way a chemist views a system in relationship to work done and all of that. These are things you are going to be studying, but they are not things you need to know at this level. But for now, you need to know that when you are trying to examine anything in life, it becomes a system. Anything that forms the immediate environment or anything that forms the outside component of that thing you are studying becomes or forms part of the surroundings of that thing. So that is what a system and a surrounding is. Now that we know what a system is, let's look at the various types of systems we have. And this is also a past question. Types of systems. Types of systems. Now, generally, we have three types of systems. We have what we call the open system. The open system. Now, what is an open system? So, just as the name suggests, open. So, when we say a system is an open system, what it means is that there is exchange of matter and energy with the surroundings. That system is exchanging matter and energy with the surrounding. And you're asking, what am I saying? So, let me give you a classical example. So, as you are studying now, your mother prepares a hot tea and places the tea on your table. You begin to hear the scent of the tea. That is matter. And you also you will be seeing that the steam would be moving away from the tea into the surroundings. So that is heat that is moving. After some time, the tea gets cold. After some time, the tea gets cold. So what that means is that there has been an exchange of matter and energy with the surrounding. The matter component is the scent you are hearing. The energy component is the fact that after some time the tea gets cold, and that was because the tea was opened, and so there was exchange of matter and energy with the surrounding. So the tea becomes the system. So an open system is one in which there is exchange of matter and energy, or sometimes you see heat is the same thing with the surroundings. Yes, you can say that. That is also correct. He has direct interaction with its surroundings. He has direct interaction with its surroundings. So one in which there is exchange of matter and energy with the surroundings. So we can give an example like the one I just stated. Let me say that uh, an open. Let me put it this way. So example, an opened cup of hot coffee. Yeah. So this an open cup of hot coffee is an example of an open system. And the reason is because there is exchange of matter and energy with the surroundings. In other words, there is a direct interaction or connection with the environment or with the surroundings. Now, two, we go on to look at another one we call a closed system. A closed system. A closed system. Now, what is a closed system? An example of a closed system is what we observe when you place water in, or let me say, your rice. Let me even use your rice cooker. That will be more relatable. Rice cooker. How does a rice cooker contribute to a closed system? Now you'll notice that when you are using your rice cooker, I don't know which one you use, but for mine, you do not see the steam coming out. But at the end of the day, you would come to realize that whatever it is you are cooking gets hot. Now, let's look at what we are looking at over here. The steam which is going to constitute the matter does not escape, but still, whatever it is you are cooking gets hot. In other words, if you are looking at, let's say, hot water in a flask, a vacuum flask, you notice that the hot water was well covered in the vacuum flask. Or let me even say hot coffee. Let me still use the same coffee example in a vacuum flask. You do not sense, or you are not hearing the scent of the coffee from the vacuum flask, which means there is no exchange of matter, which is why you are not hearing any scent. But you will come to realize that after some time, the hot coffee in the vacuum flask gets cold. If it has gotten cold, then it means there has been exchange of heat or exchange of energy. But since you are not hearing the sense, it means there was no exchange of matter. That makes the system a closed system. So in a closed system, there is exchange of heat, but not matter. There is exchange of heat, but not matter. So these are things you need to know. I hope you are clear. Okay. So let me write that. So let me just write exchange of heat or energy, because heat is a form of energy. We've already discussed that in our last meeting. Exchange of heat, but not matter. An example can be hot water in a flask or hot coffee in a flask. Hot coffee in a flask. So know that here we cannot say the interaction is direct. Here there is an indirect what? Interaction. Your question will be, sir, is there any interaction at all? Yes. The interaction is the point where there is exchange of heat. But what makes the interaction indirect is the point where matter does not also get exchanged. So in this case, there is an indirect interaction. But in the last system, there is no interaction. And what is that? Isolated system. So in an isolated system, here there is absolutely no exchange of heat and energy with the surroundings. And this is a bit difficult to achieve practically. Those that appear as isolated system exist as isolated system for a short period, but not for a long period. And I'll tell you how. So no exchange of matter and heat with the surroundings. With the surroundings. There is no exchange of matter and heat with the surroundings. So since you brought the word direct interaction, let me try to put that here so that when studying, it will be very easy for you to connect. So here we said there is direct interaction, and then here it is indirect. And then in the case of isolated systems, there is no interaction because there is no exchange. So you can meet this in section A. Why is an isolated system described as having no direct interaction? That's because there is no exchange of matter and heat. So here there is no interaction, absolutely no interaction. So what then is an example of an isolated system? And a classical example of an isolated system is a vacuum flask or a well-lagged calorimeter. I'll explain them. And this is also a question they like to ask. A vacuum flask or well-lagged calorimeter exists as an isolated system for a short period. Exists as an isolated system for a short period. Now, What does the word lagged means? So when, of course, a calorimeter is a device that is used to measure the heat content of a system. A device used to measure the heat content of a system. Know this very well. So if you recall, differences between heat and temperature. Temperature is measured with a thermometer, but heat is measured with a calorimeter. It's measured in a calorimeter. Now, when we say it is lagged, what does it mean? What it simply means is that we cover the calorimeter with an insulating material like, let's say, foam, so that there will be um, there will be a denial of heat transfer between the system, which is the calorimeter, and the surrounding. So it's like you have a calorimeter and then you use foam to wrap the calorimeter, so that when you put something there, you sort of extricate it from having direct connections with the environment, so that it doesn't easily lose heat with the surrounding. That's simply what it means. So the essence of lagging is to prevent heat loss in simple terms. Why do we lag calorimeter? To prevent heat loss or to reduce heat loss. Because you cannot absolutely prevent heat loss. Definitely some amount of heat will be lost to the surroundings, but not that much. So why then do we say a well-lagged calorimeter, or let me say that a vacuum flask is an isolated system? We say, and of course, it exists as an isolated system for a short period. We say this because no matter how good your vacuum flask is, when you place water in there and the temperature of the water or the coffee is, let's say, 80 degrees Celsius, yes, it will be able to hold the temperature for some time. But you cannot tell me that forever the temperature will still be 80 degrees Celsius. Some are very good. They can even maintain a temperature for almost 24 hours, depending on how well it is lagged for 24 hours. But definitely it will reduce. So in that case, the vacuum flask taking some time before there is exchange of matter, or let me say that exchange of heat with the surroundings, causes it to be described as an isolated system. But in that case, it exists that way for a short period, because after some time, definitely heat will be lost with the surroundings. So a vacuum flask is an isolated system for a short period. Why? Because whatever it is you put in there, it wouldn't be able to maintain the temperature forever. And once there is a slight reduction, however small it is, if there's a slight reduction in temperature, then it means that there has been exchange of energy with the surroundings. And that is why it becomes an isolated system. So that is it for the types of systems that we have, the various types of systems that we have. Okay, so now let's move a bit deeper into the real lesson. Already you know what heat is. We said that heat is a form of energy that moves from one place to another as a result of temperature difference. Heat is a form of energy that moves from one place to another as a result of temperature difference. Another terminology you must have heard. Oh, sorry, please. Another terminology you must have heard is enthalpy. Enthalpy. Do you have an idea what enthalpy is? Okay. And keep this very well, because anytime someone wants to, you know, um, analyze you as how sharp you are, these are some of the questions they ask you. Words in chemistry that are very, very similar but are not the same. So in physics, we talk about speed and velocity, distance and displacement. When you come to chemistry, you talk about temperature, sorry, enthalpy and heat. What is the difference? Let me practicalize it first, then we'll look at the difference between the two. Now, when I give you money, the money I am giving to you is heat, because you said that heat is a form of energy that moves, that moves from one place to another as a result of temperature difference. So when I give you money, that is heat. Now, when I come into your mobile money account or your bank account, the amount of money you have in your account is enthalpy. So, Osman, I'm asking you, if I want to know how much richer you are, is it going to be dependent on how much you give out or how much you have in your account? Do you understand my question? Okay. So I'm saying that when I give you money, that is heat because I'm transferring something to you. And you understand that heat moves from a higher thermal region to a lower thermal region. So that is money I am giving to you. Now, when I come into your mobile money account and I calculate the amount of money you have in your mobile money account, or let me say in your bank account, that becomes enthalpy. Now, if I want to know how rich Osman is it going to be based on the money he gives out or based on the money he has in his account? Good. So, what it means is that if you want to know the heat content of a system, or if you are doing calculation to know how much energy is in a system, would you want to use the heat or you want to use enthalpy? Okay, so you answered first, but I think you didn't get the analogy. You are going to use the enthalpy. Now, the enthalpy tells you the total heat content in a system at constant pressure. It's just like the total money you have in account. You indicated that the money the person has in his or her account is what you are going to rely on. It's what you are going to rely on to say the person is rich or the person is poor. And the amount of money you have in your account in the context of chemistry is called enthalpy. So what that means is that enthalpy is more accurate, or the money you account is more accurate to determine how rich a person is compared to how much the person gives out. So enthalpy calculation gives you a better appreciation of the heat content in a system than when you are merely trying to measure how much is going in or how much is leaving. Are you getting me? If I sit by you and I see you sending money to people and I want to use that to determine how rich you are, it will be difficult. Because for all you know, you have 10 cities and you have sent 9 cities to someone. And another day, somebody sends 8 cities to you. So what it means that in your account, you are only playing with 10 cities. So it's very difficult to tell how rich you are. But when I use enthalpy, then it means that I am going into your account to check how much that is in there. And by knowing how much that is in there, I'll be able to tell how rich you are. So enthalpy is more accurate than merely knowing how much is entering or leaving a system. So when we say enthalpy, it is defined as the total heat content of a system at constant pressure. At constant pressure. The total heat content of a system at constant pressure is known as enthalpy. So what it means is that enthalpy takes into consideration, it takes into consideration the internal energy, the pressure and volume of the system. I won't go deeper at the level of the system. So enthalpy is more accurate. If you want to know how much heat is present in a system, it is better to use the enthalpy than to just use how much heat is leaving or entering the system. That wouldn't help you to get a better appreciation of the system. So that is what enthalpy is. Now, in chemistry, we say things like enthalpy change, enthalpy change, and sometimes we even hear standard enthalpy change. What is the difference between them? We are going to be looking at it. I'm trying to take the lesson somewhere because of the calculations we are going to be doing. So I want you to get a certain understanding before we start with the calculation aspects. So enthalpy change. Enthalpy change. Now we now know what enthalpy is. What then is enthalpy change? Oftentimes, the symbol of enthalpy is H. So let me put that here. The symbol is an H. And in enthalpy change, we see delta H. We know that delta means change in something. So enthalpy change. Now, when there is a change in something, it means there is an initial and somehow there is final. That is one side. The other component is that something is being taken out of something and then something is being added to something. Another way we can also look at what? A change in something. So when we say enthalpy change, we are looking at something that occurs during a chemical reaction. In a chemical reaction, two things can possibly or likely take place. Heat can be taken in by a system, and also heat can be given out by the system. When a system is taking in heat, or when a system is giving out heat at constant pressure, then that heat taken in or given out is called the enthalpy change. So in simple terms, we say that it is the heat energy, let me say, okay, so giving out or taken in by a system at constant pressure. That is what enthalpy change is. Heat that is taken in or given out at constant pressure. Now, we look at standard enthalpy change. So I've told you what enthalpy is. I have come down to tell you what enthalpy change is. And now I am coming down to tell you what standard enthalpy change is. So standard enthalpy change. And the symbol of this is delta H phi at the top. Standard enthalpy change. So whenever you hear the word standard, usually in chemistry, you are looking at standard conditions. And standard conditions, depending on the context, we are looking at 298 Kelvin temperature. We are looking at 1 atmosphere pressure, or let me say 760 millimeters mercury pressure, or maybe 101.325 kilopascal. Those things. That is simply what it means when you hear standard, oftentimes in chemistry, or when you hear standard conditions, that is what we mean. So the definition of standard enthalpy change would be the same as enthalpy change, but with a little amendment. So what is that amendment going to be? So we say that it is heat energy given out or taken in by a system at constant pressure at standard conditions. At standard conditions. So at standard conditions of 298 Kelvin temperature and a pressure of 1 atmosphere. And a pressure of 1 atmosphere. So here you see that the word standard has come. So in redox reactions, we have electrode potential. Then we have standard electrode potential. So once the standard comes, then in your definition, we must see that standard conditions.